a few years ago, on a flight to Korea that Peter was on, and Peter, many of you have probably met him. He was the dean of our division. He retired in June, but he's still teaching math in the math department. He was on a flight to Korea, and the pilot gave the passengers a problem to solve with the promise of a prize for the winner. And the problem was to guess the number of gallons of fuel that the jet would use in its 13-hour flight, not including takeoff, because takeoff does use a little more fuel. All right, so the hint was that it had used 25,000 gallons of fuel in its first 4 hours. The only hint. So Peter is psyched, probably the only math teacher on the flight, and that prize was going to be his. So I want you to think about this problem, work in your groups, and go through the questions here. See if you can come up with an answer. Okay, for number 1, how did we find an answer of how much fuel was used? Many approaches. What are some that you guys took?
25,000 divided by 4.
So you've kind of found a constant rate of use. Yeah. Whoa, that's not how I have that set up. All right, so 25,000 gallons, right? Divided by 4 hours is going to give us a rate of gallons per hour being used by the plane. So what does that come out to? 6,250 gallons per hour. Okay, and then it's a 13-hour flight, so we can just do 6,250 times 13 hours. And what's that come out to? 200 what? Thank you. Okay. So if I was going to draw a graph that shows the total number of gallons of fuel used as a function of time, so I'd put time here, fuel used here in gallons. At time 0, we're going to say 0 gallons of fuel are used. Or I guess we could start. We used some amount at takeoff, but we're just not really thinking about it. So, and then we have a constant rate. So what does the graph of a function that has a constant rate of change look like? A line, yeah. So it's just going to go up like that. So now I want to redraw this graph with the total number of gallons of fuel used as a function of time, with an important hint that fuel, when they load it up on the jet, it weighs something close to 126,000 pounds. So what does that tell you about the amount of fuel it's going to take to move the plane? It's going to go down. At first, it might be more than we expected because 126,000 pounds is a lot. But then why is it going to go down? The plane's going to get lighter as you burn the fuel, right? So we're going to have sort of the same starting point. We burned some amount of fuel at takeoff. And then we're going to continue to burn fuel. So it's going to be an increasing function, right? The amount of fuel that we use has to go up and up and up and up. But it's going to go up slower and slower and slower. So how can I change the shape of the graph to indicate that burning less and less fuel as we go? Yeah, logarithmic shape. So it's going to be increasing, but it's going to be bending sort of downwards. Looks like a logarithmic function or maybe a square root function. It's got that same kind of shape. So we're increasing. We're increasing, so the number of gallons we use is always going up, which makes sense. You can't stop using fuel, and you can't get fuel back that you already burned, so it's always going up. But it's going up slower and slower and slower, and that causes this bend down idea. Would this change our answer to question 1? Yeah, because question 1 was a line that went up really fast. With something, would have looked something like that. And so it would be a way overestimate, right? Yes. It depends on your assumptions. Yeah. So I started it there because I said, well, we're starting our measurement right after takeoff, and we used some amount of fuel at takeoff. So that little jump is just fuel used at takeoff.
Using the, if you go by the linear, that's a 0. And you're able to find the slope.
Yes.
That's given.
Uh-huh.
If you go
So, okay. Uh-huh. Yeah, it does. Yeah, so if we start measuring time, once we've hit like cruising altitude, then yeah, we would start at 0. I guess it depends on when you mark time t equals 0. Okay, so yes, it's an overestimate. Okay, so we're gonna have a quick look at this GeoGebra file. So this is our two graphs, one linear and one non-linear. Increasing but bending downwards, called concave down. So this is the more accurate one. And after 13 hours, the line predicts way more fuel usage than the nonlinear model. Okay, so let's take a look at some highlights of the syllabus, which I handed out already. So again, my name's Caitlin. My office is just down the hall here, so if you ever need to stop in, feel free. It's North 419, or call or email me. Okay, the textbook is Calculus Single Variable 6th edition by Hughes Hallett. However, many people emailed me asking about the 5th edition. The 5th edition is totally acceptable. The 4th edition is probably fine, but I don't. I can check. I'm pretty sure there's one down there, but I'll go look. Yeah, and there's one in the math studio. Yeah. So on the last page of your syllabus, I put homework, and I figured out what problems correspond in the 5th and the 6th edition. So if you have the 5th, do the problems on the left column, and if you have the 6th, you do the problems in the right hand column. I didn't do the 4th, sorry. You'll just have to match them up yourself. Okay, so you can get the 5th or the 6th. You need a graphing calculator, just a TI 83 or 84. You don't need a big fancy 89 or 92. Yes, Casio is fine, except I don't know how to work it. So okay, it's fine if you know how to use it. Totally okay. Okay, you can read the catalog description yourself. I'm assuming you read it at some point when you were deciding to sign up for the class. So what to expect? So homework questions should generally be asked during office hours before class. If there's something that everyone's having trouble with, I'll go over a problem during class. But generally, we're going to need all the class time that we have to just cover the material for Calc 1. All right, so we're generally going to start with a lecture, introduce some new concepts for the day, and then that'll be followed or intermingled with some opportunities to work in your groups and try out the new concepts and get some familiarity. And then at the end of class, I'll assign a set of homework problems, and homework for a given week is generally due on Wednesday of the next week. So this week, we're meeting Wednesday and Friday. So that's you're going to have 2 assignments. Both of them are going to be due Wednesday of next week. Okay, so homework's always due on Wednesdays, but there's like a week lag. It's all the homework from the previous week. Yeah. Yep, there's definitely a copy in the Math Studio. I believe there's one on reserve in the library. If there's not, I'll put one there today. I think the 5th one is in there. Yeah. The 5th and the 6th editions are incredibly similar. Yeah, right. Okay, so does the due date make sense? Okay. So, oh, if you need a special accommodation, extra time, whatever, let me know. We can figure that out. Conduct, just be generally respectful. All right, resources for extra help. Well, there's me. You can always email me. I check my email several times a day. Stop by my office hours, which are listed on the front here. Other students in the class are going to be a huge resource. You should get some names and numbers of your classmates, form study groups, work on homework together. The Math Studio is a great place to do that because it is staffed all day by GCC instructors, math instructors. On our Moodle site, I'll put up a homework forum so you can post things in there to ask your classmates, or I'll monitor it too and answer questions as they're posted. The peer tutors, hold on. So the peer tutors, the Math Studio, Moodle is going to have everything that I ever give you or write or say is going to be posted in Moodle. Okay, so all handouts, videos of all the classes, the notes that I write on the board, it'll all be in Moodle. So that is a really handy resource if you ever have to miss class, or a class just went over your head. Go back and rewatch and reread. Oh, sorry. Cross out Pearson Tutor Center. Sorry about that. And the Smart Thinking is an online tutoring website that GCC subscribes all of our students to. So it's 24 hours a day, 7 days a week. You can go to Smart Thinking and get help from a professional tutor. And we're not using MyMathLab, so cross out MyMathLab tech support. And then I put the link up for GCC tech support for email, Moodle, stuff like that. I do send emails to the class a lot. Well, not a lot, like, a few times a semester if I forget to tell you something in class or something. So you should check your GCC email, or have your GCC email forwarded to an account that you do use, which there are directions for how to do that, I believe, on this help desk website. Okay, so academic honesty, don't present others' work as your own. That's all. You're totally allowed to work on homework problems together and discuss them, and projects and discuss them, but your final product, what you write, should be your own write-up, your own thoughts. All right, so for your grade, it's going to consist of homework, quizzes, projects, tests, and a final exam. And that says weekly quizzes, but they're not weekly. There's going to be 9 quizzes over the 15-week semester. So homework, quizzes, projects, tests, and a final exam. So the projects, there's going to be 8 of them, and there'll be a folder in Moodle. I'll post them all today so that you can see them whenever you want. And the due dates and the dates of quizzes are on the next page, which is the schedule for the course. But before we move there, I should mention makeup policy. I don't accept things late. If homework is due on Wednesday, and if you don't get it in, it's just going to be a 0. But I will drop your lowest 2 homework grades and your lowest 2 quiz grades at the end of the semester. So this is our schedule for the semester. Tentative. This can always change if we need an extra day on something, or if there's a snow day. And if it does change, I'll just print out a new one and you can just replace this with the new one. And then, like I said, on the last page, homework. This is the homework up until test 1. I'll give you a new one after the first test. with 5th edition and 6th edition homework problems. Anyone have questions on the syllabus? All right. So getting back to the big packet of lecture notes here. Calculus is the study of change. If a change in one thing causes a change in another, calculus is probably lurking behind the scenes. For example, if you toss a pebble into a lake, you'll create a circle whose radius increases as time passes. And as a result of the increased radius, the area of that circle increases. So a change in the radius causes a change in the area, and calculus is what allows us to precisely analyze and describe these changes and how they're related. Okay, so we're going to look at this quick clip of a soccer goal. It's called a bicycle kick. So if anyone is a soccer fan, you know what that is. But it's going to happen somewhere over here. So keep an eye out. Play. So it's kind of like an over the head. So pause it in 2 spots. We could measure the angle of his leg in the 2 different spots. So we would say, okay, at t equals 30 seconds into the video, the angle of his foot is like here, right? And then maybe at t equals 30.07 seconds, something like that, we measure the angle of his foot like here, something like that. And then we would look at the difference. We went from here to here, measured this angle, get the change in the angle divided by the change in time. Change in theta divided by change in time would have to come out to 2,000 degrees per second. So rates of change, in particular instantaneous rates of change. So we calculated here an average rate of change over a very small time interval. An instantaneous rate of change is like at a very moment in time. How fast is that angle changing? Those are the heart of Calculus 1, and that's what we're going to be studying throughout the course. Rates of change, instantaneous rates of change. All right. Here's kind of an interesting sciencey thing. Maybe some of you will know where this is headed. So what happens to the temperature of the water in a lake as you swim deeper? It gets colder. Where's the coldest water in a lake? At the bottom. So when a lake begins to freeze, what part freezes first? The top. Well, that's weird, right? It's coldest at the bottom, but the ice forms on the top. You'd think that the bottom would hit freezing temperature first and it would freeze, right? It doesn't. So something's going on. And it has to do with volume and density. So for temperatures between 0 degrees and 30 degrees Celsius, the volume in cubic centimeters of 1 kilogram of water at temperature T, and we're letting T vary from 0 to 30, is given by this formula, this cubic formula. Okay. So we're going to enter this into our calculator. And take 60 seconds to try to find a good window and graph it. So do that at your All right, so if we're trying to find the window, This model for volume only applies for temperatures from 0 to 30 degrees Celsius. So I'm going to have X min and X max go from 0 to 30. So now the Y min and the Y max, which is the V here, that's the trickier part. Anybody come up with anything good? Good choices, make a good viewing window. Nothing yet? Okay, so let's try negative 10 to 10. That's always a place to start. That was a terrible choice. So $999 to 1,000. Ah, that's good. Yeah. Yep. That's great. I was actually going to suggest that we look at the table and plug in a few values for X and see about how big they are. If you plug in 0, we'll get the Y-intercept of 999.87. If we plug in 10 degrees, we get 1,000. 20 degrees, we get a little over 1,000. 30 degrees, just a little bit more over 1,000. So maybe we'll go from 998 to say 1,005. Okay, so does that make sense? X-axis is temperature, Y-axis is volume of 1 kilogram of water. So what happens is the volume decreases until a certain temperature, and then it starts to increase. Then volume increases. Go away. Okay. All right, seemingly unrelated exercise. I want to solve this equation. This quadratic equal to 0 for all t's between 0 and 30. Use your calculator, use a quadratic formula. Don't use a graphing capability to find this solution right now. Just use a quadratic formula. Okay, and store your answer on your calculator as z for 0. Give you a couple minutes to do that. 3.9665. And I just typed the whole quadratic formula directly in because I didn't want to have any rounding error by doing small pieces of it at a time. So typed it all in, get 3.9665. I want to store it as the letter Z. So if you're using a TI, to store stuff, you use this STO button right above on. And then we're going to store it as the letter Z, so we hit alpha and find the Z, which is above the number 2, and hit enter. So why in the quadratic formula there? The quadratic formula is negative b plus or minus, right? The square root of b squared minus 4ac, blah, 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 blah. Why did I only do the plus? Because, yeah, if I were to put in the minus, this number, the 0, would not come out between 0 and 30, which is my domain. So I just have to do the plus. But you could double check. And I can do it without having to retype everything by pressing second enter and change that to a minus. See what I get. 79.5 is outside of my domain of 0 to 30. Okay, so Z was approximately 3.9665. Start in our calculator. All right, so now I want to fill in this table to find the volume of water at some various temperatures. And I want to fill in the blank with the answer to my previous question. So I have 0 and I have 30. I want to do 3.9665 also. I want to find the volume of water at this mystery number, right? So this is a mystery equation. I didn't tell you where we came up with it. But it gave us this 3.9665 number. And I want to store all three of my answers as A, B, and C respectively. So I go to my calculator. Your calculator knows function notation. So remember, I still have the volume formula in Y1, and I would like to know the volume at these various temperatures, these three temperatures. So I could use my table, right? Or I could use the function notation. So if you go vars, yvars, function y1, calls y1 into your home screen, and then you just put parentheses 0, and it's going to plug 0 into your formula. And we get the same thing if we use the table. If I plug 0 in, you get 999.87. The reason I'm doing it in the home screen is because now it's easy to save this number as A, because it's in my home screen. So store as the letter A. And then I'm going to do this again. Except this time I'm going to plug in 3.9665. And I get 999.7446. I'm going to store this as B. And I should write these down. I've got 999.87 and 999.745 approximately. And then at 30 degrees, plug in a 30 here. We get 1003.76. And I want to store that number as C. Store alpha C. Yep, so you hit vars, then you cursor over to yvars, then choose function, and when you choose function, it gives you a list of all your y. Okay, so let's see if we can pull some of all of this together here. We want to use this table to create a tight window of the graph of the volume function. So 0 to 30, is good for Xmin, Xmax, and then we're just going to tighten our window up. We went 998 to 1005. We're going to go a little tighter. So I'm going to go 999.5, maybe just a little bit below my smallest, and then just a little bit above my biggest. So maybe I'll go 1004. And now you can really clearly see it's a dip, right? We hit a minimum value here. This is a low point on the graph. The smallest volume of the water occurs at some temperature right here. Okay, and then I want to copy my graph, and I want to label the 3 points from my table with their coordinates. So okay, so here's my graph. I'm going to use my calculator to help me find the coordinates at the 3.9665. So I'm going to go to calculate value, option 1, and type in 3.9665. And it looks like it's at that very low point. 3.9665 is the low point of my graph. So this point is 0,999.87. And at the far right here, this is my point 30, 1003.7 something. And this very low point, this minimum, is 3.9665, comma, and the Y value was 999.745. Okay. So what temperature water has the least volume? That is, what temperature water takes up the least space? Water that is 3.9665 degrees takes up the least amount of space. So what temperature water has the greatest density? .9665, because you have the most amount of water in the smallest amount of space. Yeah. So density is the amount of stuff you can put in a given amount of space. Right? So it's the same here. It's 3.9665. That is the densest water. Okay, occurs at 3.9665. It feels thicker, right? Denser, harder to move through. Yes, it says what temperature water has the greatest density. So this sometimes is a little hard to wrap your brain around, and you have to, like, with water, this was weird for me to think about, but with other materials, it makes sense. We know that, like, wood expands and contracts with temperature, right? The materials you build a bridge out of expand and contract with temperature. That's why some bridges you see have those little things like this so that they can expand and contract. So lake water expands and contracts with temperature, and it gets its smallest at 3.9665 degrees Celsius. It's most dense right before freezing temperature. Once it freezes, it expands. This model only tells us information from 0 to 30 degrees. So 0 is the freezing point, right? Yeah. Yeah, right. Yeah, so as it approaches freezing, it starts expanding again. All right, so we want to talk about how a lake freezes and why the temperature we found is the key to life in lakes and oceans. Now, if water at the bottom of a lake froze first because it's the coldest, it would just kill everything in the lake, right? And so the whole way that animal life and plant life survives in a lake over the winter is that it lives below the ice. It can still swim around and have a nice life waiting for the ice to melt, right? If it froze from the bottom, that would be disastrous. Nothing would be able to live in there. So what happens is, as the temperature gets colder, the water gets denser, and the denser water sinks to the bottom. And I'm kind of forgetting how this works. Denser meaning more water, smaller space. So density is the amount of stuff you can put in a fixed amount of space. So I'm going to have you look it up. We can move on. Look up how lake water freezes. And you can read about how the density, some water sinks and some water rises, and it ends up pushing the water that's frozen to the top because it's less dense than the 3-degree water. Okay. So the ice is less dense than 3-degree water, so it ends up being pushed to the top. do we got for time here? Okay. All right, here's a more traditional application of calculus. We're looking at analyzing graphs of functions. So in this case, the function doesn't represent any particular thing. It's just a random function. So first, a definition that we're going to return to soon enough. A point on a graph is called a critical point if the graph is flat at that point. So for example, what would the critical point be of y equals x squared? Where is that graph flat? 0, 0. Yep. So my critical point happens at x equals 0. So on your graphing calculators, I want you to graph each of these equations and record how many critical points it has, how many flat spots. The standard viewing window, Zoom 6, should work for all of them. And you can divvy the equations up among your groups if you want, but pass your calculators on so everyone can see. And then leave the last column blank for now. For right now, just graph the equation, record the number of critical points. Thanks. I'm going to talk about it in just a second. So how many critical points does the first equation have? 2. 2 flat places. How about the second equation? 2. Third? 1. Fourth? Fifth? And the last one? 1. Okay. So we've all seen the quadratic formula before, right? Okay, we used it earlier in class. It says if ax squared plus bx plus c equals 0, then x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That quantity under the radical, b squared minus 4ac, is called the discriminant. And it tells us information about how many zeros the graph of a quadratic function has. So it determines whether the graph of a quadratic function has 0, 1, or 2 x-intercepts. Right? If that thing under the radical sign is negative, that means you have no real solutions, which means you have no x-intercepts. If that thing under the square root is 0, it means you're going to have exactly 1 real solution, so you have 1 x-intercept. And if the thing under the square root is positive, you're going to have 2 real solutions because of the plus or the minus, and you end up with 2 x-intercepts. Right? So any parabola can have 0, 1, or 2 x-intercepts. And that is determined by the discriminant. Okay, so the general cubic equation is ax cubed plus bx squared plus cx plus d equals 0. So very similar to the general quadratic. Right? And to determine whether the graph of a cubic function has 0, 1, or 2 critical points, you calculate a value called the cubic discriminant. Right? It comes from another formula that I'm not going to bother you with. Okay? Calculate that quantity for each of the cubics that I had you graph before and fill in the last column. And then see if there's what is the relationship between number of critical points and discriminant. Okay, so let's see what people got. What did you get for the first discriminant? 28. Okay, how about the second? 96? Is that what other people got? 108? Okay. Got a lot of 108s. And how about the third, fourth? How about the third one? Fourth? Yeah. Next one? 0? Okay. How about the last one? 0. Okay. So, do you think that there's a relationship between the discriminant and the number of critical points? So, yeah, tell me what you're seeing. Okay, it looks like if it's positive, it has 2, and if it's not positive, it has 1. Now, if this is analogous to the quadratic thing, it seems like 0 should be a special case. Discriminant of 0 would be a special case. So maybe we should go back to some of these equations and make sure that there's really only one critical point. So let's check. I'll check one of the ones. I'll check this one, and I'll check one of the zeros, this one. So I've got negative x cubed plus 3x squared minus 5x plus 2. That actually looks like it doesn't ever get flat. Right? There's no flat place. It's sort of always decreasing. So I think that this one has 0 critical points. And I'm guessing probably the next one also has 0 critical points. Let's check that one. 5x cubed minus 2x squared plus x plus 5. Also, no place where it gets flat, always increasing. So this one has 0 critical points. And then the other two do have 1. So now, what do you think the relationship between discriminant and number of critical points is? Yep. Yep. So negative it as 0, D negative, 0 critical points, D positive, 2 critical points, and D 0, 1 critical point. All right. Oh, we're past time.